In business, we are usually trying to look at how things change over periods of time rather than just one specific moment in time. And so in this lesson, we're going to talk about how this works with small changes called marginal analysis. And we've touched upon this in previous lessons, but now we're going to practice some more. We'll look at things like how much extra money we make or spend when we sell or produce one more item. We're going to also keep talking about making the most out of profit and spending the least. And then we're also going to look at some new ideas about how much stuff to keep in stock and how demand for products change. So here's the official explanation that the author of the book has provided. But to break this down into plain language, the marginal revenue measures the approximate revenue change per unit item sold. So it's the derivative of the revenue function. So here's our notation here. The derivative of the revenue function, that's R prime. And then it could also be stated as MR for marginal revenue. The second item is marginal cost. And again, here's the official explanation that the author has provided. But to break it down very simply, the marginal cost measures the approximate cost change per unit produced. So it's the derivative of the cost function. And then here are the symbols that we're going to use, the notation. We have the derivative of the cost, or we could have MC for marginal cost. The last item is marginal profit. And so marginal profit is going to measure the approximate profit change per unit sold. And so it's the derivative of the profit function. And then here is the symbolic representation. We would have P prime because it's the derivative of the profit, or MP for marginal profit. Looking at the first example, it says the revenue realized by a company on sale of X units of its product is given by this revenue function. So X is the number of items and R is the revenue. So if we want to find out how much revenue we're going to make for so many items, I would plug in X as the number of items and it would give me the revenue. So the question is asking us to find the values of R of 70 and R prime of 70 and then interpret them. For R of 70, it's asking us to plug in 70 items into the revenue function to determine the revenue. When you plug in 70 into this revenue function, you're going to get 373,800. So this means that when the company sells 70 units, you're going to get a revenue of 370,800. Now, if we plug in 70 into the derivative would be where we take the 3 down in front, we would have 3x squared plus 8x plus 160. So when we plug 70 into the derivative, what we're going to get is 15,420. So this means that if the company sells 70 items, the increase in revenue when we sell the 71st item, our revenue would increase by approximately 15,420. That's a lot of moolah for selling one more item. And then also there's a note down here that says we could also list R prime 70 as marginal revenue of 70. So this is just another notation we've got to get used to. So that was an example of marginal revenue. Let's go on and talk about marginal cost. So example 2 is marginal cost. We have the cost to a company to produce X units of a product given by the cost function. So X is the number of units. We plug that in and we get out the cost to produce it. We're going to compute and interpret both cost of 600 and the marginal cost of 600. So this notation here means just to plug 600 into the cost function. So that would go in here. And when we do that, we're going to get 11,425. So this means that when the company produces 600 units of its product, whatever it's making, it's going to cost them $11,425. Now to find the marginal cost and interpret, that's the derivative of the cost function. So I would bring the two down in front. I would get negative 0.07x, and then this would give me 40, and then this would disappear. The 25 would be 0 when we take the derivative because that's a constant. So if we plug 600 into the derivative and we get -2, that means that if the company increases the number of units by 1, so they make 600 units and they want to know approximately how much it's going to cost to make the next unit, it says it's going to decrease by $2. So that's a good thing. When your cost decreases, obviously that's good. So you like seeing negatives here. However, if you're looking at profit or revenue, you don't want to lose money on those. So we want profit and revenue to be positive. The notation could also be listed as MC and then 600 in the parentheses because the MC stands for marginal cost. The cost to a company to produce X units of a product is given by this cost here. So we have 0.02x to the third minus 0.5x squared plus 10x plus 150. The revenue is given by this function here, which is negative 1.1x squared plus 41.5x. If P of x represents the profit of the sale of X units, compute and interpret P of 20 and P prime of 20. So the other two questions directly gave us the equations that we needed. They gave us the cost function, they gave us the revenue function, and we just needed to take the derivative. In this example, they're not directly giving us the profit function, which is what we need to take the derivative of. But they do give us enough information to figure it out. We know that the profit is the revenue minus the cost. So I would take R of X and then subtract C of X. So I would list that all out. Now, when you're subtracting C of X, remember that you're subtracting every term. So don't forget to distribute that negative. When you clean that up, you're going to get a profit function of negative 0.02x to the third minus 0.6x squared plus 31.5x minus 150. So now when we take the derivative, we're going to get negative 0.06x squared minus 1.2x plus 31.5. So now we have what we need. We have the profit function. That's after we clean it up, that's this row right here. And then after we find the derivative, that's this equation right here. So if we want to find, where did it say? We want to find P of 20 and P prime of 20. So we're going to plug 20 into the profit function. That's this one here. And we're going to get 80. So this means that when the company sells 20 items, then it's going to make a profit of $80. Now, when we plug 20 into the derivative, we're going to get negative 16.50. So this means when the company produces and sells one more unit, if you start at 20 and then you want to increase to 21 items, so that is going to be a decrease in profit by $16.50. And then the additional notation would be MP of 20. That's the same thing as prime, P prime of 20. This is marginal profit of 20. So now we're going to look at profit, revenue, and cost optimization. And we've done examples like this previously, but this one is going to be a lot more work and more detailed because in the previous examples we've worked on, the equations were given to us, the equations that we needed. So in this example here, we want to maximize profit, but we have to come up with our revenue and cost functions in order to find the profit function and then take the derivative. So it's a lot more work, and I'm going to take you through it step by step. So I'm going to read it through once, and then we'll go back and pick out the information that we need for each part. A company estimates that it can sell 3,000 units each month of its product if it prices each unit at $75. However, its monthly number of sales will increase by 20 units for every 0.25 decrease in price. The company has fixed costs of $350, and then on top of that, they have a cost to make each item that is $4.20. Find the level of production that maximizes the company's profit if the company must produce and sell between and including 1,000 and 7,000 items. Then we also need to find the maximum profit. Okay, so in order to find the profit, we need a revenue and a cost function. So we're going to start with revenue. Revenue is when we take the price and we multiply it by the number of items. So the price in this case, the information, I'm going to highlight it so that you can find the information in the question easier. So anything that's related to the price, I'm going to highlight in yellow. So we have 25 cents decreases in price, and we're starting at $75. So each product is going to be initially priced at $75, and then we're going to make 25-cent decreases to see what happens. If we look at this as the initial value, and we look at this as a constant rate of change, this is linear. So this is our starting point. So this is our B. So that's the B for our linear model. And then the change in price, which is a decrease, would be our slope. So here's our change in price. And because it's a decrease, we got to make sure that we put a negative in front. So the X is going to represent the number of times we make a 25-cent decrease. So for example, if we're starting at $75 and I want to make two 25-cent decreases, I would plug in 2 for X. That would bring me down by 50 cents. So then my price would then be $74.50. So here's our price function. Now let me change colors here. All right, so now I'm going to use green for the number of items. So we're starting with an initial value of 3,000 units. This is what we think our approximation is for each month. But then it goes on to say that every time we make a 25-cent decrease in price, the number of items will increase by 20 units. So we're going to start at 3,000. That's like our initial value, our B. And then 20 is going to be our slope because that's the change in the demand based on the number of 25-cent decreases. So here's our slope. Here's our initial value. So here is our formula for the number of items. So the revenue is what we get when we take the price times the items. When we multiply that out, we get a revenue function of negative 5x squared plus 750x plus 225,000. Okay, now for the cost, I'm going to use blue. For cost in this question, it's talking about variable costs and fixed costs. Now it says that the company has a fixed cost of $350. So no matter what, we're going to get charged $350. That's our fixed cost right there. Then it also says the cost to make each item is $4.20. So however many items it is, we would want to multiply that by $4.20. So here's our 420, and we're multiplying it by the number of items. Now, we already figured out what the number of items is. That's this up here. Remember, we calculated it when we needed the information for the revenue. So our number of items is 3,000 plus 20x. So I'm going to take $4.20 and multiply it by the number of items, which is 3,000 plus 20x, and then I add the fixed cost. Now, when we simplify this, we'll have to distribute the 420 and then combine like terms. And when we do that, we get 84 times x plus 12,950. So now to find the profit, we need to find the revenue, which was what we found right here. So that's minus 5x squared plus 750x plus 225,000. That's this, and then we have to subtract the cost. And we found the cost function was 84x plus 12,950. So that goes in here. Now remember, when you subtract, you have to subtract every term. So when we combine like terms, we get negative 5x squared plus 666x plus 212,050. So this is our profit. Now we can maximize our profit. We have a profit function, so we're going to take the derivative to try to find the maximum. When I take the derivative of this profit function right here, I'm going to get negative 10x plus 666. Now to maximize it, to see if we can find any relative maxes, we're going to set this equal to 0. So that's where the tangent line would have a slope that's 0. And then solve for x. And I get that x would be 66.6. Now, remember what this x represents. This x represents the number of times we make a 25-cent decrease. In previous examples, and I should say a lot of examples, that x represented the number of items. In this example, it's not. So we have to be careful and remember that. So when we find the number of decreases that we need to maximize the profit, we get $234,227.80. So this is a potential maximum where x is 66.6. So down here, I started making a chart so we can keep track of this. So right now we have a relative max at 66.6 for x, and we need to find out if that is additionally the absolute max. We want to make sure that we're looking at the largest profit we can find on this interval between 1,000 units and 7,000 units. So to find any other possible points that could lead to a maximum profit, we need to check our endpoints as well. So I listed them here. We have the number of items, that's 1,000 and 7,000. And again, this is an x. The x is the number of 25% decreases. So we have to do some more work to figure out what x is to plug into the profit. We know that the number of items is 3,000 plus 20x. We found that over here earlier at the beginning when we were looking for our revenue function. And so if I know that there are 1,000 items, and this is equal to the number of items, I'm going to set up an equation so that I get 1,000 is equal to 3,000 plus 20x and solve for x. So when I do that, I find that the corresponding value for x when we have 1,000 products is minus 100. Now I'm going to do the same thing to find the corresponding value of x for 7,000. Since the number of items is 3,000 plus 20x, I'm going to create an equation. So I have 7,000 is equal to 3,000 plus 20x and solve for x. When I solve for x, I get that x is 200. Now, we didn't quite go over how we got this number here, so let's back up a second. When x is 66.6, meaning 66.6 decreases of 25 cents, I put that 66.6 in for this x here so we could find the number of items. And when I took 3,000 plus 20 times 66.6, I got that the number of items was 4,332. So now that we have all of our x's, we have the corresponding value for the number of items. Now we have to plug in x's negative 100 and 200 into the profit function to find the corresponding profit. When I plug negative 100 into the profit function, I get 95,450. When I plug in x's 200 into the profit function, I get that the profit is 145,250. So looking at our endpoints plus our relative max, it looks like our relative max is the highest value for the profit on that interval between 1,000 and 7,000 units. So we can now label officially that this first row here represents our maximum profit. So this would be our maximum profit. This would be the number of items we need to produce to make our maximum profit. And then X would be the number of 25-cent decreases. So now we're going to talk about something called economic order quantity, and the abbreviation for that is EOQ. And this is a formula that basically helps businesses figure out the best amount to order so that they don't run out of stock, but they also don't hold on to too much inventory, which ties up money that could be used elsewhere. It basically balances the cost of ordering inventory with the cost of holding the inventory or storing the inventory. Let me walk you through what these variables mean so you'll know what you need to plug in where when you're using this formula. So D in this formula is the demand rate, and that's how many units you sell or use during a given period. That's your D. And then S is the cost per order. So that's basically if you have to ship it or if you have to hire someone to help you do the paperwork or to make phone calls to track something down for the order. It's any cost related to the order. So that's your S. And then H is the holding cost per unit. So that's the amount that it costs to store the inventory. And it's over a time frame, and it's usually in years. So let's look at an example of how we can use the EOQ formula. It says the company anticipates selling 3,200 units of its product at a uniform rate over the next year. So this is going to be our D in our formula. It's the amount that we plan to use or sell in the next year. Each time the company places an order for X units, it's to be charged a flat fee of $50. So this is our ordering cost. That would be our S in the formula. And then the carrying costs are $32 per unit per year. So that's our holding cost to store it in our factory or warehouse, whatever. So that's going to be the H. So when we plug all of that in and solve for X, we get 100. So that means that we found that the company should place 32 orders. The last topic in this lesson we're going to discuss is called elasticity of demand. So here's the official definition, and basically what the elasticity of demand tells us is how much people change their buying habits when price changes. So if the demand for a product changes a lot when the price changes a little, then we say that it's elastic. So, for example, if we're talking about the price of an ice cream cone at an ice cream stand, if the price of the cone goes up just a little bit and people start cutting back on going to the ice cream stands and purchasing ice cream with their family, then this is considered an elastic demand because a small change in the price of the ice cream cone changed how much people wanted to purchase ice cream cones. Now, if the demand for a product doesn't change very much when the price changes, then we say it's inelastic. So, for example, if the price of gasoline goes up just a little bit, but people still need to go back and forth to work and do their errands, they might not change their buying habits of gas. So then in that case, it would be considered inelastic. Now, the point elasticity of demand is when you want to find the elasticity of demand at a specific quantity and a specific price. Take negative P, which is the price, and divide it by the quantity, and then multiply it by the derivative. This would tell us what the percent change is for the demand for each 1% change in the price. So let's look at these situations here and how the first and second derivative are interpreted when we're thinking about elasticity. So if the first derivative is negative, meaning it's decreasing from left to right, but the second derivative is positive, this is basically telling us that we have a downward sloping demand curve, meaning the demand decreases as the price increases. But because it's concave up, the decrease in quantity changes slowly as the price rises. Let's look at the second scenario. This would be where the first derivative is positive and the second derivative is positive. So this is going to tell us that the demand curve is increasing, meaning as the price increases, the demand is going to increase. And this is kind of an unusual situation. This doesn't happen too often. This is in the case where you might have luxury goods or strong brand loyalty that even if the price goes up, the person is still going to pay. So maybe a fur coat. Sometimes as these luxury items increase in price, it makes it more appealing to certain people, so they still go out and buy it. But this is rare and it doesn't happen much, but it was worth talking about. Now, the next scenario is where you have the first derivative is positive and the second derivative is negative. This is where the quantity of demand increases as the price increases, but it increases more slowly over time. So this usually happens when we're trying to buy essential goods from products in highly competitive markets. The last scenario is where we have the first derivative is negative and the second derivative is negative. So this is basically suggesting that consumers are very responsive to price changes, and so they reduce their spending when they see a price increase. So I have some more explanations broken down here. When the elasticity is greater than 1, it's going to be considered elastic demand because as the price increases, this is going to lead to a negative demand, meaning people are going to buy less. Then if we have an elasticity that's between 0 and 1, this is considered inelastic. When we have a positive price change, meaning it's increasing, this is going to lead to smaller negative demand changes. So the demand might change, but it's not going to be by a whole lot. When the elasticity is equal to 1, this is called unitary elasticity. And so when we have a positive price change, this is going to lead to an equal negative demand change. So it's a 1-to-1 ratio. So for example, if we make a 10% price increase, then that's going to typically lead to a 10% decrease in quantity. So there's a 1-to-1 ratio for that. Let's see. And then the last one is when the elasticity is less than 0, that means as we have a positive price change, meaning the price increases, this is going to lead to a positive demand. And this is very rare. This is the case where you're going to have luxury goods and rare items. So as the price goes up, that might make it more appealing to certain people that really want those items. We have a company estimates that the weekly sales Q of its product is related to the product's price by this given function. And the price is in dollars. Currently, the price of the product is $27. We need to determine the point elasticity of demand. So here's the equation we had on one of those previous slides. We want to find the price, divide it by the quantity. That's going to be negative. Then we need to find the derivative of the quantity with respect to the price and evaluate it with P is equal to 27. So if I find the quantity when the price is $27, I need to plug it into this function here to find the corresponding quantity of items. So when we do that, we get 500. So when the price is 27, we have 500 for the quantity. So now we have the values that we can plug in for P and Q here, but now we still have to find the derivative of the quantity with respect to P. We're going to first rewrite it so that the root is written in terms of exponents. So that's going to be P to the 2/3, and we just carry the 4,500 down. Then we're going to rewrite this P to the 2/3. We're going to bring it upstairs and make that a P to the negative 2/3. So now when we take the derivative, I can bring the negative 2/3 down in front, subtract 1, so I'm going to get negative 5/3. And then when we simplify, we're going to get negative 3,000 over P to the 5/3. So we're going to swing this back downstairs in the denominator and make that exponent positive. We still have to evaluate it when P is 27. So if I plug in 27 for P, the change in quantity with respect to P is going to be a decrease of 12.35. So now we have the change in quantity in terms of the price. At specifically, the price is 27. The price is 27, that goes in here. And then we have the quantity is 500 here, and then the negative here is part of the formula. When we simplify this, we're going to get that we have approximately 0.67. So if we write this over 1 so that we can make our comparison, remember what the elasticity of demand is. This is the percent change in demand when the price increases by 1%. So when we interpret this, I would read this as when the price change goes up by 1%, the demand is going to decrease by 0.67%, which is a very small change. So now we're going to relate this to how this affects the revenue. If the elasticity is greater than 1, that means the marginal revenue is negative, which means the revenue is going to fall with price increases and rises with price decreases. So this is going to be elastic. If the elasticity is equal to 1, that means the marginal revenue is equal to 0, which means the total revenue is unaffected by the changes in price. This is the unit elasticity. And lastly, if the elasticity falls between 0 and 1 and the marginal revenue is greater than 0, then this means that the total revenue rises with the price increases and falls with the price decreases, meaning that they're going to change in the same direction. They're both going to increase or they're both going to decrease, and that's going to be inelastic. So let's look at this last example. We have, suppose for a particular commodity, your elasticity is 0.33, and that currently we have 10,000 units, and they're selling for $6 each. How does a 1% increase in the price affect the revenue? So remember what the elasticity means. So 0.33 for elasticity means if we increase the price by 1%, then the demand is going to decrease by 0.33%. So I have it listed here so that you recall and you have it in your notes that when the elasticity is between 0 and 1, the price and demand is going to change inversely. So the signs are going to be opposite. If the price increases, the demand is going to decrease and vice versa. So to determine how this is going to affect the revenue, we're going to find the price and demand before and after this change. And then we can use that to find the revenue. So price 1 I labeled here, that's the first price that we're starting with, that's $6. And the demand that we're starting with is 10,000. So if we figure out what the second price is, that's after the 1% increase, I'm going to find 1% of $6 and add it back in. That's going to give me $6.06. So the price is going to go up by 1% by starting with $6 and going up to $6.06. Now, that means the demand is going to change by 0.33% in the negative direction. It's going to be a decrease. So that means I need to find 0.33% of 10,000 and then subtract it from 10,000 so it decreases, and we get 9,967. Now don't forget, because these are in percent form, when you do your calculations, you have to make sure that you change it into decimal form. So the decimal form for 1% would be 0.01, and the decimal form for the 0.33% would be 0.0033. Now, to find the revenue before the change, we're going to take the demand times the price. That's how much revenue we would have, and that's 60,000. If I want to find the revenue after the change, then I want to take the second demand and multiply it by the second price. So that's going to give me 6,402 cents. So now, looking at the elasticity of demand, we have that it's 0.33. And after going through the changes in price and demand, we found the change in revenue. And we found that when the elasticity is 0.33, we found that the revenue increased. Now, if we go back a slide and we look, this is scenario number 3. Our elasticity of demand was 0.33, and that fell between 0 and 1, which means the change in our revenue is positive. And we just verified that here. If you get a different elasticity, you might get one of these scenarios here. It just depends on what's given to you.